Thank you for coming to this talk. So this is a joint work with my advisor, Yiling. So in this work, we study how to acquire data from self-interested individuals to estimate some statistic of a population. Let me start with an example. So suppose there's a data analyst who wants to estimate the average daily workout time of a population with n data holders, with population with n people. So she needs to collect data from these n people, but they do not have their daily workout time at hand. So they will incur some cost to record this workout time and report it to the data analyst. And we assume this cost can be arbitrarily correlated with the data. So the data analyst has a budget that she can use to incentivize the data provider to record their data and then provide their data. And we assume the data analyst does not have any prior information about people's data and cost. So the problem is how to purchase the data so that I can get a good estimation of the average daily workout time. So here is the formal model. So we have n data providers who will incur some cost to get their data. And the cost and data can be arbitrarily correlated, and these data holders are self-interested. And we have a data analyst who wants to know the mean of this data Z. And he has a budget, and he does not have any prior information. So we assume that the data providers arrive one by one in random order. So at time I, the ith data holder will arrive, and the data analyst need to decide a mechanism to purchase this person's data based on all the observed history. And after all the data are collected, the analyst will aggregate all collected information to output an estimator of the population mean. And the objective of the designer is to finally output a good estimator. So here are two examples of what I mean by good estimator. Suppose what we want is an unbiased point estimation. Then we may want to minimize the variance of the final estimator. If we want to output a confidence interval, then I may want to minimize the length, the expected length. And the designer has the constraint that you need to ensure that the expected total spending will not exceed his budget. So this is the problem we want to solve. But before I give our result, let's first look at a simpler problem which has been studied in two previous EC works. So now let's assume that we know the marginal cost distribution. So I have some sense that how much I need to spend for this data. And I want to find a fixed mechanism to purchase these data points. And my goal is to find an unbiased estimation with minimum variance. So for those who are not familiar with these two previous work, I'll show you some two naive mechanisms to help you understand the challenges here. So the simplest way is to we offer a fixed price for all the data. Then the problem with this method is that we can only get the data with cost lower than this price. So when the data and the cost are correlated, my estimation will not be accurate. Another way is to purchase the data with a constant probability. And I reweight the data I observe to get an unbiased estimation. But this method may not be optimal in the sense that it may not minimize the variance of this final estimator. So Roth and Shuran propose a mechanism to like optimally purchase the data. So the mechanism works as follows. The idea is basically to purchase different data with different probability and prices. So when a data provider arrives, I'll first ask them to report the cost. And based on this cost, I'll purchase the data with a probability. If I decide to purchase the data, I'll pay him a price. Also depends on the cost. If I decide to not purchase the data, then nothing will happen. And the observed data, we set observed data equal to 0. So when we use a mechanism like this, the data provider can misreport the cost, like to maximize their own utility, but we can always get unbiased estimator that looks like this. So what we do here is we reweight the observed data. We divide the observed data by the probability of observing it, and then output the mean. So this estimator will be unbiased. So our goal is to find the mechanism that minimize this final estimator, minimize the variance of this final estimator. And because the agents are self-interested, we need to guarantee that the mechanism is individually rational and is incentive compatible, and we need to ensure the budget will not exceed the limit. So the previous work has shown that this problem can be formulated as a use a mathematical program, and they have solved the optimal mechanism. So here we use OBT and CB to represent the optimal mechanism when we need to purchase n data points, and C is the set of the cost, and we have a budget of B. So here's the plot of the optimal allocation rule from the previous work. So basically, the optimal mechanism purchases data with higher cost with a lower probability. So let's now move to our original problem when we don't have any prior information. So it's more challenging to design mechanism when we don't know the cost, because we don't know what is the optimal mechanism. But we still need to make the purchasing decision at each round without knowing the future cost. And we still want to satisfy the budget constraint and optimize the performance. So this necessarily requires us to adjust the mechanism based on the observed costs. So here's the contribution of our work. So we design a mechanism when there's we don't have any prior information. And the performance of our mechanism is not going to be worse than the benchmark by more than a constant factor. So the benchmark is the optimal mechanism when we know the cost distribution at the beginning, which we introduced before. And we also extend our result to confidence interval estimator. So here's how our mechanism works. So at each round, we'll purchase data with a survey mechanism. So at round I, I'll first post a survey mechanism, and the data holder will know the mechanism and report his cost. And we decide the probability to purchase the data. And suppose now we are at round I, at the beginning of round I. We want to collect purchase the data of the I's data holder. So we first assume that the cost of this data holder is the highest possible cost, so which denoted by C bar here. And I'll compute a approximately optimal mechanism as if that I'm now using a budget of BI to purchase the first I person's data. So the formulation of this approximately optimal mechanism is basically the same as the optimal mechanism when we know the cost we introduced just now. And it can be solved efficiently. Then I'll use this server mechanism to purchase the data. So again, the data holder will report his cost, and I'll purchase the data with some probability. And I continue with this process, and finally I'll output the unbiased estimator we introduced just now. So I reweight each data point and output the mean. So is this mechanism clear for everyone? Okay. So we show that when we use a mechanism like this, and we set the budget we use at round I to be proportional to the square root of I, our mechanism will be incentive compatible and individually rational, and it satisfies the budget constraint. And its performance, it will be no worse than a constant factor times our benchmark, which is the optimal mechanism when we know the cost distribution. So here's the ideas, the main steps of our proof. So we'll first decompose the variance of the estimator into per round loss. So so the variance of the estimator is roughly equal to the loss I incurred at the sum of the loss I incurred at each round, and this loss is just the expectation of 1 over the probability of that I purchased that data. And then we only need to to compare the performance of our mechanism. We only need to compare this loss function with the optimal mechanism. So so to do this, we'll prove two properties of the expected loss of using this mechanism. So the first property is about how the loss will change when I change the budget I use. So it basically says that when I decrease my budget by a factor of k, then the loss of the mechanism will not increase by a factor larger than k. And so this is really is a straightforward result by the definition of our loss function. And our second property is about how the loss is going to change when I only partially observe people's cost. So suppose now at round I only observe first I people's cost. So this is their cost is a random subset of the overall cost set. And if I use all my budget to purchase these I person's data, then my expected loss will not increase, will not get higher. Based on these two properties, I can prove that when I allocate budget BI at round I, my expected loss will not be larger than the benchmark times the ratio between the total budget and this budget allocated. So then our problem basically becomes a budget allocation problem. So we want to decide this BI at each round to minimize the total loss. And we can prove that when we choose BI to be proportional to the square root of I, my total loss will not be larger than a constant times our benchmark. So here BI is the how much I'm going to use to purchase the first I person's data. So the average budget I allocate for each person is proportional to 1 over the square root of I, which means that I will use more budget when the estimation of the cost is less accurate, like at the earlier rounds. So we also extend our results to the confidence interval estimator. So So when what we want is a confidence interval, we don't actually need the estimation to be unbiased. Sometimes it could be beneficial for me to ignore some high-cost data so that I can reduce the variance of this estimation. But I need to add a bias to compensate the error. So we'll have some bias variance trade-off when we decide the mechanism. Yeah, so our objective here is to minimize the expected length. So we consider a modified server mechanism that can ignore the data. So when data point comes, again, I'll ask him for his cost. And then I'll, with some probability, just ignore this data point. If I ignore the data point, I'll need to add a bias to the final estimation. If I'm not going to ignore that, then I'll use the same survey mechanism to purchase the data. And purchase data and then reweight the data. And then we can construct a confidence interval with this collected data. So we give the characterization of a two approximation of the optimal confidence interval mechanism. So basically, the mechanism will ignore the data with virtual cost higher than a threshold. And we also design a online mechanism that matches the benchmark within a constant factor. So again, the benchmark here is the optimal mechanism when we know the cost distribution. Yeah, so that's all of the talk. Thank you.